Have you ever wondered how your car just knows when someone's in your blind spot? Or how a drone can zip through a forest without hitting a single branch? Well, a lot of that magic comes down to one core technology, FMCW radar. But it turns out, not all FMCW radars are the same. So let's dive in and break down how this incredible tech evolved, step by step from a simple distance finder to a full-blown 3D perception system.
And that brings us to the big question, right? If the basic job is just to measure how far away something is, why on earth are there so many different kinds? The answer is really about evolution. Each new type is a clever solution designed to tackle a more complex problem, to help us sense the world in a much richer way.
All right, before we get into all the different flavors, let's just make sure we're all on the same page with the core concept. FMCW stands for Frequency Modulated Continuous Wave. Now, the key idea here is the chirp. The radar sends out a continuous signal, but its frequency is constantly changing, usually ramping up. When that chirp hits an object and bounces back as an echo, the radar compares the frequency of the echo to the frequency it's sending out at that exact moment. That difference is called the beat frequency. And here's the magic trick. The bigger that difference, the farther away the object is. Simple as that.
Okay, so every technology has to start some way, right? It has a level 1. For FMCW radar, that starting point is the sawtooth waveform. It's the simplest, most direct way to use that chirp principle we just talked about.
The way this works is incredibly straightforward. The radar's frequency just ramps up in a perfectly straight line. That's our up chirp. As soon as it hits its peak frequency, bam! It just snaps right back down to the start and immediately begins the next ramp up. It looks exactly like the teeth on a saw, hence the name. And the important part is, only that clean, steady upward ramp is used to figure out how far away things are.
So, the beauty of the sawtooth method is that it's simple to build, and it's pretty good for basic range finding. But, and this is a big but, it has one huge limitation. You see, that beat frequency it measures gets affected by two things, the object's distance and the object's speed. That speed part is due to the Doppler shift, like how an ambulance siren changes pitch as it speeds past you. A simple sawtooth radar can't tell the two apart, so it gets confused. Is that a slow object that's really far away, or a fast-moving object that's much closer? That ambiguity is the exact problem the next evolution needed to solve.
So how do you solve that puzzle? How do you untangle range and velocity? Well, you need more information. And that's exactly what the next generation of FMCW radar was built to do. Give us a crystal clear picture of both an object's distance and its speed. And the solution they came up with is just brilliant. It's so elegant. Instead of a ramp up and a sudden drop, the triangular waveform uses a smooth up chirp followed by an equally smooth down chirp. So now you get two different beat frequency measurements for the same object, one on the way up and one on the way down. And with those two pieces of data, you can solve for your two unknowns. You can finally separate range from velocity. Problem solved.
And this capability is so important. For a car, it is not enough to know there's something up ahead. You absolutely need to know if it's a parked car or another vehicle moving at highway speeds. Being able to measure range and velocity on their own is what makes features like adaptive cruise control and automatic emergency braking even possible. It's a total game changer. Okay, time to level up again. If triangular FMCW is good at measuring speed, then multi-chirp FMCW is the undisputed expert. Instead of one big up and down cycle, this method fires off a whole burst of short, rapid-fire chirps. The system then looks at the tiny changes in the phase of the returning signal from one chirp to the very next. And by analyzing those subtle phase shifts, it can get an incredibly precise measurement of the object's velocity.
So what's the big payoff here? Accuracy. Just insane accuracy. This high-quality velocity data lets us do some really advanced stuff, like create what's called a range Doppler map. This is basically a detailed chart that shows every single object the radar sees, all plotted out by both its distance and its speed. Honestly, this is the bedrock of pretty much every modern, high-performance radar system you'll find today.
So far, we've figured out how far away something is and how fast it's moving, but there's still a huge piece of the puzzle missing. Where is it? Is it directly in front of us, or is it off to the side? This is the third dimension, angle, and it's what lets a radar truly see in 3D.
This is where things get really clever. The technique is called MIMO, which stands for multiple input, multiple output. Instead of just one antenna sending and one receiving, a MIMO radar has a whole bunch of each.
Think of it like having two ears. When you hear a sound, it hits one ear a tiny fraction of a second before the other, and your brain uses that delay to know which direction it came from. MIMO radar does the exact same thing. Because its receive antennas are in slightly different spots, the echo arrives at each one with a minuscule phase difference. By measuring those tiny differences, the radar can calculate the object's exact angle. And why does that matter so much? Well, without knowing the angle, your car's brain is basically blind to location. It knows there's a threat, but it has no clue if that threat is in your lane or the one next to you. This ability to estimate angles is what creates a high-resolution map of the world around the car, turning a simple detector into a true 3D sensing system. And that brings us to the top of the mountain, chirp sequence radar. You can think of this as the grand finale, where everything we've just discussed comes together. It's not just one type of chirp, it's a carefully designed, precisely timed sequence of different chirps. This sophisticated approach lets a single radar system measure range, velocity, and angle all at the same time, feeding all that rich data into its brain for a complete 3D picture of the world. Okay, we've covered a lot of ground pretty quickly. So now, let's just take a moment to put all these pieces together and see how this entire FMCW family stacks up. Looking at this, you can really see that evolutionary path we talked about. We start with sawtooth, which just gets you basic range. Then triangular comes along to solve the speed problem. Multi-chirp takes that and makes it incredibly accurate. Then MIMO opens up our vision to the third dimension with angle detection. And finally, chirp sequence systems act like the master conductor, bringing it all together for a complete solution. You can see how each step just logically builds on the one before it. So where do you find these radars in the real world? Well, they're pretty much everywhere. They're the eyes for the Advanced Driver Assistance Systems, or ADAS, in your car. They give drones the spatial awareness they need to not crash. You'll find them in industrial plants, automating processes, and get this, they're even a key part of new ideas for using 5G cell networks for sensing the environment. So if you're going to take away just 3 things from all this, let it be these. First, FMCW radar is not one single thing. It's a whole family of solutions. Second, every member of that family came about to solve a very specific problem, from just seeing something, to knowing its speed, to pinpointing its exact location. And third, that powerful combination of multi-chirp and MIMO is really the engine driving most of the advanced radar systems that we rely on today. When you boil it all down, this whole journey just shows that FMCW radar is this incredibly powerful and flexible toolkit. It gives us this whole set of different building blocks that engineers can choose from and combine to create the perfect sensing solution for almost any problem you can imagine. And that really leads to one final thought. As these radar systems get more and more sophisticated, combining all these different techniques in new and clever ways, it just makes you wonder. With these constantly evolving tools to see the world in ways we never could before, what will we be able to sense next?